Thanks for inviting me, everyone. As I said, I'm a fourth-year PhD student at Berkeley, advised by Professor Bin Yu, so she couldn't be here, so sent me instead. And so today I'll be talking about understanding and overcoming the statistical limitations of decision trees. So let me start, I guess, a little more broadly. So I think, as we can all know, that the world is increasingly being run by algorithms, and it's used to make a host of important decisions, such as who do we give loans to, who do we give job interviews to, who do we even grant parole to in the criminal justice system. And one important case is of algorithms in important high-stakes decision-making is exemplified by the case of Glenn Rodriguez. So he was arrested, I think, in the 90s or sometimes in the 80s, I forget. And he was, sentenced to a long period of jail time. And he was sort of a model prisoner, a model inmate. And he kept going up for parole. And despite his sort of good behavior, he kept getting denied. And the reason for his denial was that there was this sort of algorithm called COMPAS that was being used, and it was used to predict recidivism, or the probability of reoffending if you're released. And when he did, and this algorithm kept giving him a high score, and despite the fact that he was this model prisoner, he kept getting this high score. And the reason for this was this algorithm was both black box, so people couldn't identify it, and there was sort of a typo in the data that was entered. So he was held for much longer than he had to be. And so this sort of leads me to the point that these sort of black box algorithms such as COMPAS are often difficult to audit, and they're often based on sort of complex predictive models such as black boxes. For example, you can have a feature vector, it produces this model, and then it produces an output label, and we don't really understand why this output label came to be. For example, the feature vector could consist of hundreds of features, and the model itself could consist of hundreds of parameters. And this can often be very useful in cases such as as we see in large language models, where the more parameters you have seems to lead to larger performance, but sometimes in high stakes decision making, we want to have simpler models. So let's take another look at this sort of COMPAS model that was used in Glenn Rodriguez's case, right? And the target that the model was predicting was, will an individual be rearrested in less than 2 years if they're released? And so it used about over 130 features, and its accuracy was about 0.66. And then there's this really nice work done by Cynthia Rudin's group at Duke, where they had a really simple model. So they built a decision tree, and they only used 3 features in their model, and then they could achieve approximately the same accuracy as the COMPAS model to begin with. And it's a really simple model. You can look at it, and you can understand exactly what is happening, right? So as I said, it has comparable prediction performance. And looking at this decision tree, you can visualize it. You can even implement it by hand. You don't need to have some extremely complex inference being done. And also decision trees, I would argue, often mirror the way people think, sort of these rule-based things, and it's kind of an easier model for people to understand. And, given, say, a particular person with, say, 2 priors, given an age of 23 and no previous juvenile crimes, it's very easy to understand what the model is doing. So you just drop it down the tree, and then it sees you reach the leaf node, which predicts arrest, and then that's what you understand the model is doing. So in other words, decision trees are often regarded as a gold standard of interpretable models, and now interpretability has many technical definitions, and it's often hotly contested. But one thing that sort of people agree upon is that decision trees are interpretable. And some reasons for this is that they can be visualized, they can be implemented by hand, and as I said earlier, they mirror the way people think. And some other reasons is that they can be audited for errors and biases. So, by looking at the model, you can easily understand, is there sort of an error? Is there a bias here? For example, is there like a racial bias? Is there sort of a gender bias? These are sort of things we can exactly examine the model for. By having these sort of easy models, you can facilitate humans in the loop. They can again, sort of building off point 1, they can look at the model and understand what is going on. And then they can also instill trust or distrust, because you can exactly understand the decision-making process of the model. And another thing is that they can, one thing we care about in scientific machine learning or in general is that they facilitate understanding and also counterfactual reasoning. And what I mean by this is, for example, if I made a change to the number, change to the age, or I changed, say, the number of juvenile crimes, I can understand what the model prediction would have been. So one reference to check out is, this work by our group, which is explaining or trying to understand what we really mean by interpretable machine learning. But this is not the only work. There's been tons of work trying to understand what it really means to have interpretable machine learning. So apart from interpretability, why do we also care about decision trees? They are sort of the basis of a number of really powerful algorithms such as random forest and gradient boosting, which achieve state-of-the-art performance on tabular data. So there was this really nice work done by a group, I believe, in Paris, which compared decision tree models, or rather tree ensemble models such as random forest or XGBoost, to a number of really popular deep learning models, and they still showed that there's still a significant gap between these sort of tree-based ensembles and deep learning models, at least on tabular data. Of course, for unstructured data, I would argue that deep learning models are still are the way to go. But again, I think understanding this gap and then thinking about this gap is an interesting research problem. But these, again, are sort of black box ensemble models, right? This sort of random forest and XGBoost are not particularly easy to understand. So there's a gap between decision trees and black box ensemble methods, or here tree-based ensemble methods. So this was another sort of empirical study done by Olson Randall and a group where they sort of applied a number of machine learning algorithms to bioinformatics problems. And here we see that the gradient tree boosting and random forest performed really well. But there was sort of a gap between the simple decision tree and then this more complex ensemble-based methods. And so another, I think, really interesting research program is, can we understand and bridge this gap where possible? Decision trees are interpretable, but these other models achieve better performance, but we don't really understand the decision-making process there. So I think the sort of setup for the talk will be, this will be sort of the framing question for the talk, which is, can we understand and bridge this gap where possible? So let me get to sort of what I'll actually cover today. So the first thing I'll be covering is a statistical limitation of decision trees. And then the second part is I'll be trying to overcome this limitation by modifying CART, or classification and regression trees, which is sort of the main decision tree algorithm that's used in practice. So before I start, let me give some very basic introduction of what a decision tree is. So, it's just a piecewise constant model by recursively partitioning the covariate space. So, for example, if you have some data here, you can think of the white labels as 1 and the black sort of triangles as 0, and you have two features. A decision tree can be formed by, you make a particular split, so x2 larger than a, it divides the covariate space this way, and then you make another split here where you have x1 larger than b, and so you have 3 leaves here, and then the prediction is made by just taking the average in each of these leaf nodes, or if you have a regression problem, by taking the average. So let me give you sort of a whirlwind tour of some of the decision tree theory that people have done, and then I'll go into sort of our work moving forward. So one important work that has been done, especially in interpretability, is sort of feature importances or feature rankings. How can we think about what features are important? And there's a whole host of work being done here. I apologize if I've missed any particular references. Another very important line of work that we'll build upon is sort of point-wise or non-parametric consistency for CART and random forest. And this was sort of started, I would argue, in the sort of last decade when people really tried to understand this algorithm. And then lastly, also moving from just prediction, can we also think about sort of inference or asymptotic normality for random forest? And this has been very important, for example, in the field of causal inference, where people are often thinking about what sort of inference guarantees can they provide for important parameters such as average treatment effect or heterogeneous treatment effects. Okay, so, but I would argue, again, that the non-parametric consistency does not sort of address the performance gap between trees and these sort of black box models such as random forest. Rather, in order to understand these gaps, we need to sort of study the inductive biases, or rather, the weaknesses and strengths of decision trees. And in other words, what are the assumptions the algorithm makes or does not make to predict on unseen data? So what kind of structures do decision trees perform well on, and what kind of structures do decision trees perform poorly on? And one way we're going to do this is we're going to study the inductive biases via a set of generative models and then try to understand when decision trees do well and do poorly. So as I said, let me get to the first part, which is sort of understanding how decision trees perform, what some of the limitations of decision trees are. So this is joint work with Yansho Tan, who's a professor now at the National University of Singapore, and been my advisor at UC Berkeley. So the first sort of observation we made is that trees are sort of inefficient at expressing additive structure. So what do I mean by this? Let's take a really simple model here. You have a really simple generative model, which is the sum of two sort of Boolean interactions. The first one is just if x1 is larger than 0, and the second one is sort of an interaction term between x2 and x3. So arguably, the best way to sort of express this model is the sum of two decision trees. So one is, you just have one split on x1 or one tree on x1, and then you capture the interaction between x2 and x3 on the second tree. And then if you were trying to compress all this model, all this information into just one tree, you would have to make sort of this repeated split. So you would split on x1, and then you would split on x2 again, and then finally split on x3. So there's sort of this repeated subtree structure. And then, what I'm going to go forth to saying is that the degrees of freedom is equal to the number of leaves. So in the sort of more concise model, you only have 5 degrees of freedom, whereas in this sort of more complicated tree where you only have one tree, you have 6 degrees of freedom. So let's just actually see what happens if you look at, say, the test set mean squared error for cart, which is just one tree, random forest, which is like an ensemble of cart trees, and gradient boosting, which is sort of sequentially, you can think of as sequential cart trees. So just built on the residuals of each of the previous cart trees. And I'm going to fit each of these models to a simple linear model here where I have 50 features, but only 20 of them are used. So it's a sparse linear model. And then if I look at these rates here, I'll see that cart actually has a pretty poor generalization rate as compared to the number of samples, especially compared to random forest and XGBoost. So how do we go about analyzing cart or a number of decision trees? So basically, you can break down cart or every decision tree algorithm into kind of two steps. So step one is I'm going to grow the tree. And step two is I'm going to make predictions by averaging the responses over each of the leaves, right? So you can use any algorithm you'd like to grow the tree. And then generally, most decision tree algorithms, they just predict the average response in each of the leaves. For example, in regression, you can just predict the average response, or in classification, you can take the majority label or something like that. And so you can decouple these steps using sample splitting. So what I mean is that in step one, I'm going to use half the samples to grow the tree, and then half the samples to make predictions. So again, if you're sort of familiar with causal inference, this is very, very commonly done in causal inference, and it's sort of known as the honesty condition, where you use half the samples to grow the tree, and then half the samples to infer whatever parameter of interest, such as the average treatment effect. So in this talk, I'm going to focus on the second step. So I'm going to assume that we're sort of given the tree structure to begin with, and then I'm going to talk about the statistical limitations of making predictions by only averaging the responses over each leaf. Does the setup make sense here? Otherwise, I'm happy to stop for questions.
Like, have people tried linear predictors of the leaves? Like, let's say I want to do linear regression there.
Yes, so people have tried sort of like doing, making predictors that, you can fit any model to each leaf node. But I'll show that despite doing that, you will still not be good. So what's the precise goal that I'm going to come up with, which is the generalization lower bounds for trees on additive generative models. So what do I mean by this? So the generative model I'm going to consider is the following. So this is kind of the first line here, y is equal to fx plus epsilon, is your typical statistical learning setup. I just have some regression function plus some noise. And then the precise structure I'm going to assume on the regression function is that it's the sum of some additive functions. So I'm going to assume some sparsity S here. So it only depends on S sort of coordinates. And then the next thing I'm going to assume is that X is drawn from some distribution on the hypercube. And then I'm going to assume homoscedastic noise as well as mean zero noise. And then I'll point out that this drawing X from the hypercube is without loss of generality since trees are invariant to rescaling. So this is a completely general sort of assumption on the covariate distribution. And then what is the set of estimators I'm going to consider? Here, I'm going to consider the set of estimators f hat of n, where, again, I'm given the tree structure. So someone has built the tree structure for me. And then I'm going to impute it, or I'm going to impute each of the leaf nodes with some training data. And then the quantity I'm going to study, or the quantity that I'm going to provide the lower bound on, is the squared error risk. So now I'm going to get to the main result. And then once I state the main result, I'll provide sort of a proof, a sort of easy sort of proof structure that we follow. So if you assume that each of the component functions is C1, so it's and it has some minimum derivative. So this is, for example, satisfied by just a linear model. So if f of x is a sparse linear model, then for any tree t, so again, this is not the rate that I'm going to talk about does not depend on how you grow the tree structure. You grow the tree structure how you'd like, then I'm going to achieve the following rate. I'll unpack the rate here, but what I'd like you to just focus on is that it sort of depends on n to the minus 2 over s. So it's not a particularly good rate. So for example, if you want to achieve a certain rate, you'll kind of need an exponential number of samples. So how can we compare this, say, to the minimax rate that people have sort of identified for additive models? So this is the rate that I just presented on the previous screen. So there was a work done about 10 years ago now by Garvesh, Martin, and Bin, where they established the minimax rate for C1 additive models. And they sort of get a rate that's about s times n to the minus 2/3. And this is kind of achievable by penalized kernel methods. So as I was saying earlier, this is sort of polynomial, whereas ours will be exponential, or rather decision trees will have an exponentially worse rate than sort of the minimax rate here. Great. Any questions so far? Cool. So as I said, so this is also the n to the minus 2 over s plus 2 rate is the minimax rate if you do fully non-parametric regression. So it achieves this rate, but it's much, much poorer than the minimax rate for C1 additive models. So as I was saying earlier, if you look at the test set mean squared error for CART, random forest, and XGBoost, and you look at this model where you have about 20 features, you'll see that the lower bound that we predict has a slope of about minus 0.09 in terms of the number of samples. So CART almost achieves that. And the random forest slope is about twice that. So it's sort of an open question what the lower bound for random forest is, but perhaps a guess is that instead of the minus 2 over s plus 2, it'll just be minus 4 over s plus 2 or something like that. But this is sort of an open question, and we don't know exactly how to establish it. So now let me get to the proof structure, and then once I get to the proof, then I'll talk about the second part of the talk, which is can we actually overcome some of these limitations. So the proof ingredients consists of 2 steps. So I think with most statistical proofs starts with a bias variance decomposition of the risk. And then the second part is we're going to connect decision trees to information theory. Specifically, we're going to interpret trees as a lossy code, and we're going to connect it to rate distortion theory. So let me start with the first part, or the bias variance decomposition. So again, this is the setup or the statistical model that we're studying, right, where you have this sort of generative model, and then you have an estimator, which just consists of leaf nodes, or this partition of the covariate space, right? And I'm going to present this is a proposition about how we can decompose the risk. So you can sort of upper bound and lower bound the risk by this following quantity. I'll break it down as following. So the first part is the bias. So this is, the bias achieved by this estimator here. for a given tree. And it's basically, you can sort of think of it as a sum over all the leaf nodes in the tree, and then the conditional variance of the model of the generative function for those leaf nodes, and then multiplied by the measure of that leaf node to begin with. And the second term is kind of interesting, and it's kind of intuitive, which is that the variance for this particular thing is just proportional to the number of leaves divided by n. And you can think of this as the number of leaves as sort of the number of degrees of freedom of this model. So for a linear model, you can think of this as, instead of the number of leaves d, it'll just be kind of the number of covariates to begin with. Okay, so now let me move on to the second part. But before I do that, I'm going to give you just a kind of a whirlwind tour of rate distortion theory, and then I'm going to connect it back to the lower bounds that we're studying. So, basic sort of setup of, say, information theory is you have some sort of input x, you throw it into an encoder G, and you have sort of a code book which is sort of measuring, this is what you're mapping it to, and then you'll pass the encoder's input will be passed to the decoder, and then you'll have a decoded input which is called x hat. So it takes in, G will take in the input, and then it will decode it as following. So this was a theorem established by Shannon, I think in 59, that there's sort of a trade-off between the size of the codebook and how well you can recreate the input, or rather the distortion. So if you measure the sort of distortion by taking an expectation over this distribution, with some weighted, for some weighted norm beta, and then Shannon showed that, if your distortion is less than some value d, then the size of your codebook must be at least 2 to the r, where r is this rate distortion function, and it's here it's the infimum of the mutual information, where you're taking the infimum over all conditional distributions such that the distortion is d. Is there any questions about this slide or any of the previous slides? Okay. In that case, let me think about how you can think of a tree as a lossy code. So if you have this sort of tree model, where you have 3 leaf nodes, you have an input x, right? First thing you'll do is you can drop the input down the tree. You can encode it as the leaf index. So in this case, if it goes to 2, you just call it L2. So here the size of the codebook is 3, and then you'll decode it as the centroid. So rather the centroid of that particular leaf node. So you can think of a tree as a lossy code. It takes an input, goes into a codebook, and then outputs as the centroid here. And then here, again, so here m is the number of leaves, where this is the size of the codebook. The distortion is how close the input is to the centroid. And here, hence the number of leaves, for a given distortion will be 2 to the r, where r, again, is the rate distortion function. So that was just thinking about the inputs x. How do we actually bring in the responses y? Because we're actually thinking of a regression problem. We're not just thinking of we're trying to bound the squared error, right? So I won't get too much into the details, but if you use some basic calculus and the lower bound, the derivative of the lower bound is bounded by some beta for each of those component functions, then you can show that the bias squared is larger than some quantity delta. And then I'm going to put all of the the ingredient 1 and ingredient 2 together. And so if you have this proposition, which is that it's bounded by some quantity beta and the bias squared is delta, and I have this rate distortion function, and if I combine it with this bias variance trade-off that I had in the first slide, then I'm going to get that the squared error risk can be bounded by infimum over the distortions for some d, plus this variance, which is sigma squared 2 to the r over n. So basically what I've done is I've replaced the bias term with the distortion, and I've replaced the number of leaves with 2 to the r, where r is the rate distortion function. And then, I'm not going to get too much into it, but then going from the rate distortion to sort of the theorems that I presented is pretty easy, and there's been work done, and you can sort of bound it via standard calculations. So that's kind of the proof structure. Is there any questions regarding the proof structure? Okay, so let me just summarize part one before I move on to the second part of the talk, which is that decision trees are statistically inefficient at estimating additive regression functions, and this contributes to the gap between trees and black box models. This inefficiency is only from leaf-only averaging, so it's not due to the tree structure. It's because you sort of average over each of the leaves to begin with, and you're not using all of the samples. So going back to your question, one reason for this is that when you have an additive model, there's sort of a global structure to the model, right? Here, you're not utilizing that global structure. You're only averaging within the samples in the leaf, and even if you fit, say, a linear model to each of the leaves, you're not using all of the data. So you're still going to pay a high cost in the variance. You might pay a smaller cost in the bias, but I still think this sort of exponential gap will exist. And so what are the two contributions? One is that this is an algorithmic-specific lower bound, right? Again, this is holds true for any decision tree that you come up with. And two, so this is a connection to rate distortion theory. I'm not sure if it can be more broadly applied in the context of machine learning to improve lower bounds, but I think could be an interesting tool in the toolkit. Okay, let me move to the second part, which is, can we actually overcome the statistical inefficiency on additive models for decision trees? So let me go back to the slide earlier where we had trees are inefficient at expressing additive structure. Again, we know we had this generative model, which is the sum of two sort of Boolean interactions. A very simple idea is how can we just, we know that a better model is growing the sum of two trees. How can we do that? Can we come up with an algorithm to grow multiple trees? And maybe that will allow us to overcome this exponentially poor sample rate. So, but let me be more precise about what we want our algorithm to do. So we wanted to overcome, CART or single decision trees limitations where we wanted to be able to disentangle additive components. So we want to build, say, one tree for each additive component. And we also want to do this without knowing which feature corresponds to each component. We don't actually know in practice what feature corresponds to what component. But on the other hand, we do want to preserve some of CART's strengths. CART is able to sort of adapt to higher order interactions. So if you have a lot of interactions, CART is a good thing to do. And again, you want to do this without knowing the true depth of the interaction. So CART is able to adapt to the order of the interaction. And again, we want to be able to maintain interpretability. And one way to do that is we want to have a simple model or have a small number of splits to begin with. And if we are able to sort of achieve this disentanglement where we have one tree for each kind of component, then we'll hope to have improved prediction performance, fewer splits because you don't have these repeated subtrees. And also, we also have fewer false discoveries because for interactions, because we don't have additive components occurring on the same path of a tree. And people often look at the paths of a tree for understanding what features sort of interact together. So do existing sort of methods actually fulfill these sort of criteria simultaneously? No, because random forest is kind of a CART tree, but just grown on bootstrap versions. So it shares CART's weaknesses. And then if you have gradient boosting, such as XGBoost, you need the tree to have a pre-specified depth. So you often, before you start the algorithm, you provide a hyperparameter saying, I want each tree to only have depth 2 or depth 3 or something like that. And so it's unable to adapt to the true order of the interaction. And so, again, it loses CART strengths. So now I'm going to present our algorithm, which hopefully is trying to overcome these limitations and achieve what we want. So I'm going to introduce the algorithm FIGS, or fast interpretable greedy tree sums. And so what we're going to do is modify how CART is grown to grow a flexible number of trees simultaneously. So I'm going to go back to this model and show you how CART builds a tree for this model. And then I'm going to show you how FIGS will grow a tree for this model as well. So if you have a CART model here, we're trying to think about, so in the first iteration, you have, say, just a node, and you're going to have a split S, right? How are you going to choose the best split before I'm going to just define some notation, you have a node T, and then you're going to create 2 left and right children's. And the way I'm going to split this node, or the way I'm going to choose a split S, is that I'm going to maximize an impurity decrease. So what an impurity decrease does is it just kind of measures the difference in variance by splitting on a node. So I want to pick this best split such that I make the left child and right child as homogeneous as possible, and I measure sort of heterogeneity by the amount of variance in each node. Okay, so how will CART grow this out? How will CART grow this model is sort of what I discussed earlier. You're going to split on x1, then in the next iteration, you're going to split on x2, and then you're going to just keep repeating the process until you have this repeated subtrees here. Any questions about how CART grows this, sort of fits a model for this data generating process? Okay. So now let me show you how figs will fit a model here. So the first thing it's going to do is going to do the exact same thing as CART, but instead of continuing splitting, it's going to create an option to start a new tree, right? And then both of these, both the old tree and the new tree are going to compete for what leads to the best impurity decrease. So in this case, you'll see that the second tree actually leads to the best impurity decrease. So it's going to start a new split on the second tree. And in the third iteration, it's going to do the same thing. It's going to consider all the possible splits among the first tree, second tree, and starting a new tree. And then in the third iteration, what you're going to see is that, in fact, the second tree leads to the highest impurity decrease. So it's just going to do another split on the second tree. So at each time, all the leaf nodes are competing for splits, and who wins is what leads to the highest impurity decrease. And in this case, we're measuring impurity decrease in terms of the residuals of the other trees, not because you want to sort of marginalize the effect of the previous trees that have been grown. Are there questions about the algorithm? So it's a pretty simple algorithm where you just kind of modify CART in order to start a new tree at each point. Okay. And in order to actually predict, at each of the leaf nodes, we're going to predict the average of the residuals over the new leaves. Okay, and one thing to think about is sort of the computational complexity, right? So in the worst case sort of runtime is n squared r squared d, where n is the number of samples, d is the ambient feature, and r is the number of splits made. And the CART runtime here is just n squared rd. So usually we make a fairly small number of splits. So the fig sort of algorithm doesn't have particularly worse wall clock time than CART. So let me now get to some of the results, and then I'll discuss some of the theoretical and empirical results as well. So let me start by looking at the generative model. So again, we have this sort of similar generative model where you have y is equal to f of x plus some noise, and x is drawn from the hypercube. And the model I'm going to consider is the following. So I'm going to divide each of the d features into s blocks, right? Where you have so x1, x2, and x3 belong to the first block, and say the last two features belong to the last block. And I'm going to assume that each of these blocks is independent. And the model I'm going to consider is sort of a generalized additive model where I have f of x is equal to the sum of each of these, to a component function on each of these blocks. So it's kind of generalizing the additive model a little bit, where you sort of have an additive model, but each additive component depends on a block of features. And so now I'm going to sort of present like an ERM kind of model, or a little bit of an Oracle theoretical result, where you say you have a set of trees as follows, and I have a bunch of data. So these are a set of like predefined trees. And if I fit, say, an empirical risk minimizer to the data plus a sum of trees as follows, then I'm going to get the following set of theoretical results. So again, if I assume that the gradient is kind of bounded by some quantity, then there exists a collection of trees. I don't really know how to construct these trees, but such that the empirical risk minimizer satisfies the following quantity. So this is the upper bound for the risk. I'll break it down, but basically what you can think of is that the risk is sort of upper bounded by n, times minus 2 over the largest block size. So, and it's conditioned on an event, and you can think of this probability of this event goes to 0 as n goes to infinity. And so how does it compare to sort of additive models? So in additive models, each of the block size is precisely 1. Each of the component functions only depends on one feature. In that case, we see that the model is has rate s n to the minus 2/3. So now in the next slide, I'm going to compare it to the rate for one tree versus the minimax rate, right? So this is the rate that we have for additive models. And then the minimax rate for C1 is precisely, again, s times n to the minus 2/3. So this kind of model achieves the minimax rate for additive models, but at the same time, it's able to adapt to higher order interactions as what we discussed earlier. And from part 1, we had that a single tree is only able to achieve n to the minus 2 over s plus 2. So it's able to achieve this, able to escape this sort of exponentially poor rate. Any questions about the theory?
Okay, so the original theorem does not have the condition that each of the additive terms only depends on one.
You mean the tree lower bound?
Like the Rascuti result. So so you said that generalized form of the additive model, and now you're requiring that each of the terms only has one of the.
I'm saying this is a corollary of the more general theorem. So in the more general theorem, you can allow for any block size. Mm-hmm. In a purely additive model, the block size is 1. Mm-hmm. So you get n to the minus 2/3.
Right, and the Rascuti result does not have a similar.
Yes, the Rascuti result is precisely for one, so purely additive model. It's like a linear model. So it doesn't have this block size.
I see. Oh,
yeah.
Okay.
So I don't know if there's a minimax rate for this sort of block size model.
I see.
Yeah. Yeah.
The solution of the ERM tree sum is same as the solution of figs, right?
Yes, but for a fixed tree structure. Like figs also has to grow the tree structure. Then figs is doing that in a greedy way.
Okay, but the guarantees would carry over to figs if they both have the same solution, right? Otherwise,
If figs had that tree structure and then you just kind of imputed it, then you would get the same guarantee. Cool. But you're right that figs is an ERM on this space. So let's go back to sort of, that simulation that I presented earlier for a linear model. And we see that, CART has this slope of minus 0.14, and random forest, again, has this exactly twice the slope, which, again, makes me think it's minus 4 over s plus 2. And then figs achieves a much better slope. This simulation is a little confusing because it's better than the minus 2/3 rate, so I'm not exactly sure what's going on, but yeah. And so this was just all simulations. Does it actually do well for, say, a number of real-world data sets? So I'm going to study it for both some classification and some regression data sets as follows. So we have 6 classification and 9 regression. So what I'm going to do is, how I'm going to study this sort of real-world performance is for each of these, say, classification data sets, I'm going to study the AUC on the y-axis, and then I'm going to study the trade-off with interpretability on the x-axis, and then I'm going to compare it for a number of different models. So in black, I have figs, in orange, I have CART, and then I have a number of, say, popular other decision tree models, and then the sort of gray line is random forests here. So you can see here in this case that there's sort of a nice gap between actually figs and the random forest, but as well as other models. So this is the performance across a number of data sets. We see for the large data sets in particular, figs has better performance. And then for some of the smaller data sets, it has slightly worse performance, but it kind of bridges the gap between trees and black box models, especially say for the credit and readmission data set, where the gap is smaller between random forests and figs. However, on the smaller data sets, as I said earlier, we do see some overfitting, and that might be because of the sort of added flexibility of figs. But I'll also note that if you constrain the number of splits, it has no worse performance than CART. So now I'm going to get to an actual sort of empirical. Sorry, go ahead.
Sorry to cut you off. What is the time complexity for, let's say, when n is really large and like?
So you mean the computational complexity? It was n squared RD or something like that.
So when you ran it, like, is it like that's what you exactly get? So it scales exactly like that?
We didn't exactly investigate the complexity because the number of splits was very small. So it takes very little amount of time on your computer to fit the model. But I assume that it would be about n squared. Yeah. I think there's some tricks that people have come up with to like make it n log n, and you can also implement that. Like if you sort the data points before, then it's easier to make splits because you kind of just move from left to right. But yeah, that's if you want to do that, you can, I think, replace the n squared to n log n. But
it won't affect your analysis.
No. Because we're assuming that we have the tree structure given, so it doesn't really affect the analysis. Going back, so that was sort of, for sort of open source or like benchmark data sets. I like to sort of apply FIGS to a more real world sort of empirical problem here. So I'm going to use it to learn clinical decision instruments. And what are CDIs? CDIs are sort of tools to guide treatment decision for a patient-specific clinical condition. So for example, on the right here, I have, a CDI that I visualized, and it's the CDI that doctors use to diagnose abdominal injury. And one problem with building CDIs is that heterogeneity is very ubiquitous in medical data. Patients have different conditions, patients have different demographics, and we need to come up with sort of more personalized decision rules that are yet interpretable. So the question I'd like to ask, or the research question, is how can we use FIGS for CDIs in the presence of like heterogeneous data with multiple groups? So I'm going to introduce sort of a variant of FIGS, a pretty simple change. And the task is to predict whether the label Y, here the label Y is if a child has traumatic spinal injury, when there are multiple groups such as age. And the algorithm is quite simple. You divide your X matrix your covariate matrix into two groups. One covariates if it's larger than 2, your age is larger than 2, and another if the patient is less than 2. And I'm going to fit a model, say, logistic regression or something, to predict if a particular patient belongs to the larger than 2 group or less than 2 group. And then the next thing I'm going to do is I'm just going to build a FIGS model, but I'm going to build it on all the data, not just on each group. So I'm going to build a personalized model for each group, but I'm going to use all the data. But rather, I'm going to weight each sample by the sort of probability if they belong to larger than 2 or less than 2. This way, I get to use all the data, but I'm sort of personalizing to the group by sort of using sample weights to personalize for different groups in the data. And so, in other words, when I have this sort of impurity decrease splitting, I'm going to use sample weights to indicate if a sample, is there a high probability that they belong to the larger than 2 group or not. And so now let me present some results of sensitivity versus specificity for predicting spinal injury for both of these things. And I'm going to compare the specificity for fixed levels of sensitivity for different methods. So for CART FIGS and GFIGS, which is the model I just introduced. And you can look at the specificity for different results of sensitivity, and you'll see that about FIGS and GFIGS actually improves quite a bit. It improves specificity by about 15 to 27% over CART, which is a large gap for doctors in practice and allows them to be, more judicial with their resources and leads to, say, more efficient resource utilization. Last thing I'm going to do is, can we actually interpret this model? Does it actually make some sort of medical sense? So this is the clinical decision instrument that was learned by GFIGS. You don't need to focus too much on it. I'll break it down for you. One is that we worked with sort of medical professionals to show that the features used actually match domain knowledge. So these are kinds of features that doctors would actually use in order to make their decision. And then the next thing is GFIGS also disentangles different domains. So one reason why GFIGS might perform better than, say, CART is that it has this disentangling, or it separates, say, the additive structure. So for example, the first tree corresponds to symptoms or features that correspond to signs of injury. The second tree is about mode of arrival and the injury mechanism of the patient. And the last one is, say, the severity of injury. So that's all. And then all of these algorithms are implemented in a open source package called iModels. Thank you.